So, double check here. Okay, looks good. Let me 41 seconds. It's got to be an easier way. Let me just do it over here. No, that won't work. Okay. I'm gonna get started in just 1 second here. I'm just having trouble pulling up the chat feature in OBS, but I've got it in Restream, so we're all good. Okay, so I want to try out a new kind of technique I have going on here. I've got, as much as I despise PowerPoint, I've got some slides behind me. So instead of a totally blank canvas, I'll have a couple figures here. No text or anything like that. Just something that's kind of a starting point that I can sketch on that'll hopefully streamline things a little bit. So what I want to do is have some of this stuff available, these figures for like note taking. So when I'm teaching this live, I'd like to be able to hand out notes that are just blank sheets of paper that have this kind of stuff on it, so that when you're trying to feverishly write down like what I'm writing on a whiteboard, you can kind of just fill in the blanks. I think that'll be helpful, but we'll see. It's a good, this live stream is a good good trial run. So I got a couple things I'd like to talk about today. I want to discuss a little bit about coplanarity. I've got these figures up. It's been a while since I made I think 2021 since the last time I made a video about coplanarity. I'll discuss flatness at maximum material boundary, which is something that doesn't come up very often for good reason. And if we have time, I've got a lecture here about reporting basic dimensions, or why you should not report basic dimensions. So hi everybody who's in the chat right now. If you have questions, feel free to just punch them in there. It's fairly informal. Anything you might have, just punch it in there, and I'll see if I can answer it live. So this concept of coplanarity isn't exactly in one place in Y14.5. So what I mean is, it's mentioned with profile, right? If you read the whatever Y14.5, you go to the profile chapter, it will mention coplanarity. And it'll be like, hey, by the way, profile rules at coplanarity, which it does. Yeah, Adam, yeah, this will be, you'll be able to see it on YouTube afterward. I'll leave the recordings up. So what Y14.5 doesn't do very well is explain like what happens if I don't use profile, right? So we'll start with just a plus or minus dimension. The idea here, why this is bad, is that it's not clear exactly where you're measuring from, because there's no datum reference frame. Okay, and the problem with that is that yes, you do have rule number 1, but rule number 1 only applies to each little feature, right? So I can check this feature, like bang, rule number 1, we're all set. Check this feature, rule number 1, we're all set. The relationship isn't the full length, right? So, a good shop will obviously not, mess this up, but it's not clear, right? So what somebody could do is grab calipers, right? handy calipers and measure one side of this, little table or whatever, and then measure the other side with 2-point measurements, and then they can check envelope too, but you can end up with a part kind of like this, right, where each side kind of conforms, but they're not related to each other. And again, that's going to be your 2 times. So if you thought about this, like, let's take it to like an extreme here, right? You guys have seen my videos or seen me live before. I love talking about kitchen tables or tables in general. A good table maker knows that the legs of a table need to be perpendicular to the top, and they all need to be level so the table won't rock on the floor or whatever. But if you gave an alien a drawing of a table, they might not know what in the world it was, right? So if your dimensions look like this, you said 4 times whatever, 36 inches. If they just slapped it together, you could end up with a table like this, right? Where you put a tape measure on it and you're like, okay, that's 36 inches, right? That's 36 inches, right? But it's totally like non-functional. So those plus minus dimensions, I know I'm like harping on that. And if you think I'm harping, check out 2018, the Y14.5 2018. They have like a whole mandatory appendix about it, or non-mandatory appendix. They go on and on about why you shouldn't do it. So this is the coplanarity, example of that. We would like all of these, table feet to be on the same plane or within a reasonable amount, so table doesn't rock on us. Okay. So the new kind of way to do this is we give it a size, and notice there's no number of instances here. And we come in with our continuous feature symbol, right? For I can tell, the symbol's really gained in popularity. And in situations like this, it can be pretty helpful, right? You don't have to necessarily set up a datum reference frame or anything. So the idea here, what this is really doing, is just extending the perfect form envelope. It's extending rule number 1. The whole length, right? Whereas before, if we did 2 times, rule number 1 is just for each individual little area. And that word's going to come up a couple more times, individual, until we get to profile, right? So a continuous feature does what you might think 2 times does. Before a continuous feature, you might have seen notes that say treat 2 surfaces as 1, stuff like that, which might not be 100% clear, right? The good thing with the continuous feature is that it's in Y14.5, and as of 2018, it's got a very distinct meaning. Okay, so it's there if you need it. Now let's create a datum reference frame. So I'm going to do A is this little surface. We'll do 2 times some dimension. And then we're going to come down here, and probably the most obvious geometric tolerances is parallelism, right? We want those to be parallel. The problem with parallelism is that our orientation, our form, and our size tolerances are for individual features only, right? They only control one thing at a time. Now you can do you can say, hey, this parallelism applies 50 times, right? That's okay. I'm not saying, you have to literally put, 50 different feature control frames. So this, we put 2 times in front of it, fine. what it doesn't do is establish a parallelism tolerance zone between features. So our tolerance zone for this, what we could end up with is something like this. All right, we're going to have a parallelism tolerance zone of, we're saying 10 thousandths. And from an international audience, I'll try to switch to metric and start using that a little bit more in this presentation. I know I was doing it before, but it slips my mind. And then, so that's our parallelism tolerance zones, right? They're free to float, but they've got to be parallel to our datum A, right? What controls the separation of those two tolerance zones is this, right? And when we talk about profile can do the same thing as far as controlling the size and the location of the surfaces. So what's going down here is we're going to have, I know this is super exaggerated, but we've got our LMC and our MMC size, right? So I'm not saying you should never do this. I'm just saying the parallelism doesn't control the coplanarity error. Functionally, maybe this is what you want. Maybe you have some situation where, you know, a part is sitting and it needs to be parallel, and the other part, the height does not matter, but the parallelism does. You know, if you, I don't know, you don't want something rolling off the top of something, you know, it's possible. You could, I think I've seen before where people kind of try to override and say, hey, this parallelism applies to both surfaces and it controls coplanarity, whatever. Maybe in the older Y14.5s, that was a thing. Now we have the tools. So I would be very weary of putting a note where you're trying to force, you know, one of these, what I just said, orientation, form, or size, where you're trying to force those to control coplanarity, which profile does by default. Okay. Let's go to our next tolerance here. Oh, I know. I accidentally skipped flatness. That's fine. So basically the same thing applies to flatness, but I do want to show you how the tolerance zones get switched up. So with flatness, now we're not oriented to anything, right? And I always recommend when I teach this or whatnot, you don't have to memorize it. Just notice that there's no datum reference, right? There's no datum reference. We're only measuring it to itself. Ergo, there can be no orientation to anything else. So what that does effectively is our tolerance zones down here, right? Now they're not parallel to anything. So our actual surface can kind of be anywhere within our larger size tolerance as long as those surfaces are flat, right, to this number, this 10 thousandths. So again, not the end of the world. It might be what you want in your design, but it's not coplanarity. So a question here from Abraham. That means even with parallelism, we can end up one side at 1 and the other 1.02, and we're still being parallel to A. Yeah, basically. Yep. What he's asking here is if this was parallelism. Yeah, we can be at the limits of size, right? So the maximum distance those can be away from each other is 0.04 if the form, orientation is perfect, right? So that's the worst case if you just want to know what that distance could be. But again, it would require the form and the orientation to be perfect because you'd be at LMC and your MMC size limits. It was a good question. That's clever. I don't know. I guess I wouldn't have thought of that. And the chat, when I was reading it, it had this, two whatever lines. Like, oh, parallelism. That makes sense. I guess it's not as easy to do the other ones, but okay. So we did size. Let's do blank slate. We did size. We did form, aka flatness. We did orientation. We even got some continuous feature action. So now we'll get to, the good stuff, right? Profile. These are all like edge cases, right? When you have coplanar surfaces and you specifically don't need them to be coplanar in your design. Profile is automatic, right? You don't have to have any special notes or anything. If I just go, ooh, actually, this is a good spot. Let's go with metric here, or SI units. So 30, let's say 40 millimeters, basic dimension. Let me show this a little bit different. We're going to go profile. Oh, that'd be really small on SI, huh? Say profile, whatever, 2 millimeters. This is another way to show it, and I can't remember off the top of my... I'm pretty sure you can show it just on this little line right here. I'm almost certain that applies to both. Maybe you need the 2 times. Whatever, it doesn't matter. But just this, right? No datum reference. We're going to control the form, just like flatness. But why I'm basically making this video is that, right, form, aka flatness, plus that coplanarity. So our tolerance zone looks like this. And actually, I may draw that more better. So say that's the actual surface of our part. Tolerance zone is 2 millimeters. We'd obviously need some kind of other tolerance for that actual height. Where this would probably be used is maybe we're going to use this as datum A, and then we'll control up here, right, to datum A. So this is a really convenient way of using surfaces separated, about space as one datum feature. So quick question from Matthews. How about this 2 times in front of geotol doesn't establish a pattern of features forcing the flatness to accomplish? Yeah, so that's a good question. It does force. So what he's saying, I think, is that, hey, if we say 2 times, doesn't that force coplanarity? We're saying it's a pattern, treat them all the same. It does. All it essentially does with form orientation is repeat that tolerance zone, right? So you're correct that it is a pattern, but those tolerance zones are not connected to each other like it would be with profile. Like I said, you could have like a lengthy note, kind of explaining, that you want the tolerance zone to be a total, go across the this chasm right here. But you really don't need to anymore because the profile does that automatically. Oh, yeah, you can use 2 times in front of flatness parallelism. That's fine. Yeah, that's legit. Recommend it, It makes the drawing easier to read. Okay. So profile with no datum reference, right? We automatically get this coplanarity control. This is one way to show it on the drawing where we have this dashed line and we point to it. We could also have it, over here somewhere. If it's over here, I'd recommend putting 2 times in front of it to make it clear that you mean this and this. When you point to this dashed line, it's clear, it's not one or the other, it's both, right? So kind of minor detail, but you want to get those correct, you know what I mean? Okay. So we can take the profile thing like a step further. Yeah, you're welcome, Matthews. So say we do profile 4 millimeters to A. We call this A, and we give it a basic dimension. I'll say 40 millimeters. This is essentially going to do. So there's supposed to be lens. This is essentially going to do what parallelism does, except now with coplanarity, right? So before it was flatness plus coplanarity. Now it's parallelism plus coplanarity, as you might expect. But because this is basic, right? Now this is going to take over the size and the location, right? So we've got to be coplanar within 4. The overall size of this, right? Essentially, the size of this block is 42. The MMC is 42. The LMC is 38, right? Which can be kind of tough, right? You might want to control the coplanarity more closely than the size and location. And I'd assume a lot of times you would, right? If we're building, again, a kitchen table, the height can vary more than this coplanarity we're talking about. So this is, where you might say, oh, well, just make it not basic, right? We'll just do 40 millimeters plus or minus 8. Right now we can have more tolerance for the size and location, right? So what this does is if we go from basic to a plus or minus, now the size and location are controlled with their plus or minus dimension, and the profile just controls the form plus the orientation, right? So it's kind of a different way to look at it. Now, of course, we can claw that back, right? It is not recommended anymore to use plus or minus dimensions for that. So what we'd want to do here is composite profile, right? So say we want the size to vary. I think I did plus or minus 8 a second ago. So I'll do plus or minus 16 millimeters. I know it's a little excessive. And we'll do 4. I'm going A and A. Right. So now we have this top of this feature control frame is going to control the total size of this block, right? So essentially we're going to have an MMC of 48 and an LMC of 32. Oh, jeez. $32, right? It's plus or minus 8. Right? So our size is controlled up here, as well as the location of this surface and this surface, right, relative to datum A. What this controls is the orientation, right? So the parallelism plus the form plus this coplanarity, right? It makes it a little bit different from your typical composite profile. So let me draw these tolerance zones as best I can for you here. So we're going to have this very large, so we're going to say 32 millimeter to 48 millimeter. right? And those two surfaces can be anywhere within there. But now we have this much smaller, what did I say, 4 millimeter tolerance zone. It's basically just free to translate up and down. And it's not really necessary to say, oh, it can't translate. It can translate in any direction, right? Because it's a plane, right? So it can translate up and down, left and right or whatever. It doesn't really matter. But it can't rotate relative to anything. That's that datum A control, and it's going to be this plane right here. Right? So this is how you can accomplish with composite profile what a lot of people like plus or minus tolerances for, right? It can be pretty helpful. Okay. What was I going to talk about next? So let me chat. Let me find a good picture I like here. This will work. I want to chat real quick about flatness at MMB. So what I mean here is it's possible, right? I don't recommend it, and I'll try to explain why. You can have a flatness tolerance of a feature of size, right? So this block right here, instead of just saying, right, one side, I would say, hey, this is datum A. Instead of just saying one side or the other is datum A, here, right, datum A is a center plane in the middle of the part. And somebody probably screaming at the screen, like, no, it's a derived median line, or derived median plane. You're controlling the derived median plane with flatness. But when you use datum A, when you use that feature, it's a center plane. So what do I mean? Say you have, that's not a good representation. Say you have a hole in the middle of the part, and we're going to call it out to something. All right, say we're going to position this diameter, something, to A. Right, when we call out A, we're using the center plane. So the first thing we'll do is we're essentially saying, hey, the center of this part is our 0 for the translation of this hole, up and down. Now we need a datum B and all that for additional stuff there. Now, what I don't like about this is there's a couple reasons. The biggest thing I don't like is that if you have, and I guess you can make this argument with a flat plane where you have a convex surface, but if you have a surface like this, right, where it's tapered at all, and say you're going to go measure this hole, if you capture it the way you're supposed to, the way we capture this datum A at RMB, you're going to grab it in like a vise or something. If you have any taper to it like this, it can rock back and forth in the vise, and it's not really clear how you're gonna measure it. Now, you could call this out at MMB. Great. Right, even though this is at RFS, right, it's fine, right? You're using the datum, you're calling this feature, so your maximum material boundary for this feature is 2.04 plus 0.02, right? That doesn't really change. You can have a fixed boundary for that, and I guess you could gauge it. It's just, if you're going to do that, why go through the trouble of even having the flatness, right? It's probably just easier to control. It is easier to just control it. Rule number one. It's a weird situation where you're trying to control the straightness of the center, but the reason you do that is to allow more size tolerance. So you have this weird functional situation where you're saying, all right, this thing has got to be super straight, right? But it can vary in size a lot, which I think makes sense for some parts, like diameters occasionally. That makes sense. I think if you were buying a box of nails from Home Depot, right? If the diameter of the nails varied by 50 thousandths, right? Would you really notice? I mean, I guess it depends on the size, the penny scale or whatever, but probably not. You probably don't measure the nails. But if the nails are crooked, you're going to be upset, right? Because they're not going to go in correctly. So this is kind of the same thing. You're saying, hey, say if you're building a house, right? The bricks can vary in height a lot as long as they're straight, which might make sense for certain things, like if you were doing paver stones or something, maybe. But with bricks, it would not make sense at all because your house wouldn't go together correctly. So I just can't think of that many situations. And you can, put in the comments in the video if you have some application that makes sense to you. The other thing, this actually measuring this, I mean, I guess you can do it on a coordinate measuring machine, but it seems like a lot of work. You got to like gather a bunch of data and measure both sides. I just really don't think it's almost ever very, very necessary to really put this on a drawing as a primary datum, right? I'm not saying don't use center planes, but calling out flatness of a derived median plane and then calling that center plane out as a primary datum isn't ideal. Here's the other thing. I draw this taper for a reason, right? If you're allowing this size to vary a lot, which is the whole point of this, you can have a perfectly straight center plane, right? It's perfect, right? Even though you've got this crazy taper, right? As long as the balance of the mass of the material is about that center plane, you're all good, right? So it's kind of a wacky tolerance. All right, so I see I got a question coming in. So let's assume there's a square block with square hole in the center. Oh, easy. Okay, we can do that. Datums A, B, and C are simply on external walls. The hole is tolerance or yeah, that's a good question. Okay. You can play ball. So his question is, basically, we got this block. We're just arbitrarily picking a datum reference frame, no big deal. And he's saying, hey, we want to control this hole with profile of, it doesn't matter, to A, B, and C. And the question is, can I inspect it with a caliper? Sort of. So actually, let me give this a number. So what I mean by sort of is, say our profile is 40 thousandths, right? Actually, hold on. I'm pretty sure my question asker here is from Europe. So let me try. Say we've got a diameter of 40 millimeters and a profile of 8 millimeters. That is like a wild whatever. So this is basic. So we're going to have an MMC and an LMC, right? Even though it's profile. I know it sounds wacky. But our MMC, right, the smallest the hole can be, that's a diameter of 32. And our LMC, the largest the hole is going to be, is a diameter of 48. So what you can do with calipers is verify that you're not smaller than the MMC, right? Pretty effectively. So, right, say the hole comes out like this. I can get in there with my calipers and kind of verify that, make sure the hole's not too small. What I can't really do, and what makes it tricky, say we look at the hole from the other side. if I come in with calipers, I can kind of measure this minimum distance, but I can't effectively find like this measurement, right? And that's not even really easy for a coordinate measuring machine. It depends on the geometry of the hole. But that's something position lets you kind of skip over a little easier. So position tolerance, the size and the form are controlled with the size tolerance, which is a little less stringent than the profile tolerance. So the answer is kind of no. You really can't. And other than a real cursory, getting close check, you really can't with calipers. Cool. All right, guys. That's about all I had. I'll check the chat one last time, make sure I didn't miss anything. Feel free to put questions on wherever you find me on this video or LinkedIn or whatever. You can email me as well. It should be pretty easy to find. Yeah, Abraham. Yeah. Using profile in this example would mean the axis is not controlled, but the surface of the hole is right. Yeah, exactly. With profile, you're not controlling the axis. But, and this is where it gets weird, you could later say, oh, I'm going to use this hole as a datum. In which case, yes, then you would use the axis. But it wouldn't be a question of using the axis to verify whether the feature is correct. You'd just be using it later on. All right, thanks, Brian. Appreciate it. That's cool. Cool. All right, guys. I will catch you next time. Thanks for tuning in.